So, first of all, right. So let's say that I just integrate f from a to b. Yeah? Well, we can do the same operation to both sides, right? Martin, this is sort of what we were talking about this morning, right? We have a form for f, and now we can use this to get a form for the integral of f. Right? This is a forward. Right? So in particular now, we have that this is the integral, that we can give the integral from a to b of f of x dx. Well, that's what? That's f of c times b minus a. Now, this function is symmetric about c. So in fact, when you integrate from a to b, this term vanishes. See this? It spends just as much time negative as it does positive. And this is why expanding f about c is kind of a tricky way to go. Yeah? So in fact, you can ignore all of the even numbered terms. And so your next one is going to look like 1/24 f prime prime of c b minus a cubed. And I think that's like, and of course since I wrote out a bunch because I was doing it at 3 in the morning and I wasn't sure how many I was going to need. Okay, so right, so here's our integral for f of x, and what do we immediately notice? Yeah, look at this. Let me get another color here. Look at the first term. Yeah, this is f evaluated at the midpoint times b minus a. So in other words, we just showed that the midpoint method, right, which is exactly this approximation here, has error that looks like O of delta x cubed. Yeah? Got lucky. So we'd like to compare this to the trapezoidal rule, and doing so takes a little bit of trickery, and there are lots of ways you can do it. Your textbook actually suggests a very clever one, which I then stole. So let's take a look at what they do. So here, now what we're going to do is we're going to plug in our endpoints, right? Because we know that the trapezoidal rule evaluates f at the two endpoints and then kind of draws a line between those two. So let's do that. So let's plug in f of a equals f of c plus f prime of c a minus c. How many terms do I need? Plus 1/2 f prime of c a minus c squared plus 1/6 f prime of c a minus c cubed plus other stuff. Yeah? Just barely fit it in there. And similarly, if we write f of b, we're going to get, the same expression, form, with b's in it. B minus c plus 1/2 f prime b minus c squared plus 1/6 f prime c b minus c cubed plus f. Yeah? These proofs are really annoying to type up in LaTeX, by the way. So, now, what are we going to do? Well, one thing you could do, which seems kind of ham-handed, but happens to work, right, is that remember the trapezoidal rule. What does it do? It averages these two numbers and multiplies it by b minus a. Right? That's the trapezoidal rule. Well, we could just do that to both sides of the equation and see what happens. Yeah? And in fact, it turns out that this gives us the error, the optimal error approximation here. So, in particular, we have b minus a times f of a plus f of b divided by 2. Right? This is the trapezoidal rule. Right. Then what is that equal to? Well, you get b minus a times f of c, yeah? Plus, now, okay. So what happens when I add these two terms? Well, you have f prime of c in both cases. You have a minus c plus b minus c. Yeah? Let's do this over here. Yeah? A minus c plus b minus c, right? But c is equal to a plus b over 2. Yeah? So this is a plus b, right, from those two, minus 2 times a plus b over 2, which is just 0. Yeah? So in fact, if I average these two, yet again the first order term cancels, so we get lucky. Yeah? So what do we get? Well, we get that this, then when we write down the next term, we're going to have plus 1/4 f minus a. And unfortunately, it's like kind of annoying to write down. A minus c squared plus b minus c squared. Plus other stuff. Call these HOT, higher order terms. Okay. So in other words, what did we do? Well, we showed that up to third order, right? This is big. Look, notice we have that this kind of looks like delta x, these two terms. So they're delta x squared, just added together. So this whole big thing here is this big O of delta x cubed, right? You get one delta x there and two more there, and they're just summed together. Yeah. So up to cubic order, in fact, the trapezoidal rule also agrees with our expansion of the integral of f to third order. Yeah, they have the same first two terms, namely this guy and then 0. Yeah. So in other words, what I just showed you guys is that the midpoint rule also is cubic in its approximation quality. Notice that this is actually kind of a weird property, right? Because we added a second data point, right? The midpoint rule only knows f of x at the midpoint. The trapezoidal rule knows f of x on the two sides, but we actually didn't earn anything. Both methods are x cubed. Yeah? That's kind of surprising. In fact, it's a common gotcha. Like, people have warmer feelings about the trapezoidal rule because it kind of looks closer to f of x, right? It's using linear interpolation, but it turns out that the quality actually, and if you look at this third order term, it turns out that the trapezoidal rule is worse than midpoint by a factor of about 2. Yeah, in fact, can we kind of see that? Not easily from the way that I've written it down. Yeah, you have a 1/24 here, you have a 1/4 here, and a 2 there. Yeah. So so you have to be really careful when you analyze these schemes, because things that sort of by design look better aren't necessarily any better than each other. Yeah. It turns out that in general, if you look at Newton code schemes, and we don't have time to prove it in this class, all of the ones that use odd degree polynomials have the same quality as the polynomial right before, right? So we used piecewise constant to get the midpoint rule, and then we used piecewise linear to get the trapezoidal rule, and both gave us the same quality. Then if we switch to Simpson's rule, the algebra becomes infinitely more irritating, but by basically a similar proof, instead of x cubed, it jumps up to x to the 5th. Yeah? And then, what do you think is going to happen if I use 4-point closed quadrature? Remember? Or 4-point open quadrature, rather. Right? Simpson's rule is 3-point quadrature. Can anybody guess? Same thing, yeah. If I use 4-point quadrature, I'm still going to get x to the 5th. This is the pattern, right? It's like goes 2 at a time, which is surprising, right? This sort of isn't what we would expect to happen. But you know, math God surprises us in new ways every day. Okay. So of course, all of these approximation schemes that we wrote down are for a single interval from A to B, applying Simpson's rule or the midpoint rule or a trapezoid one time. Right? But as we said, really a more reasonable scheme is to do a composite kind of thing, right? Where I take my interval from A to B and I divide them into a bunch of delta x's. Yeah. So remember the width of each interval is delta x, right? Which means that the number of intervals kind of looks like 1 over delta x. Yeah. So if your error on any single interval is x cubed, then when you multiply that by all the terms you're summing up, right? Then there's going to be like a 1 over delta x number of things that you're summing. And so you lose 1 degree of accuracy, right? So if you have composite midpoint, then this is a delta x squared method. Now careful, does this mean that I should not use the composite method? I should go back to just subdividing into a single thing? The answer is absolutely not. There are 2 different delta x's, right? The delta x for composite is like when I divide my interval into a bunch of pieces, it's the width of a single piece. Right? Whereas the delta x in the previous slide was the width all the way from A to B. Right? So this is a much smaller number. Cool. So somehow analytically, this is actually pretty easy. Right? The common pattern here is you write down a reasonable scheme, and then you plug in your Taylor series, and you see which terms vanish, and the ones that don't tell you something about the fidelity of your integral. Yeah? So there are tons and tons and tons of strategies for quadrature, and they all have their own features and their own drawbacks, right? So obviously the Newton code schemes are sort of the simplest because what they assume is that you always sample your function at even points. But if we're in the case where we can actually decide where we're going to query f of x, then it might be that we actually don't want our x's to be evenly spaced. This is actually a little bit counterintuitive, but it turned out that we had the same conclusion in our last lecture about interpolation. That you can interpolate a function better if you sort of bunch stuff near the endpoints a little bit. And that's an observation due to Chebyshev back about 100 years ago. So anyway, one method for doing this would be the Gaussian quadrature method. Right? And actually this brings us back to a different way to derive these quadrature weights WI. Right? Which is that one thing you could do is say, let's say that I have a quadrature rule for 5 points. Right? So now I have W1 to W5. I could ask that my quadrature rule holds exactly for polynomials up to degree 4. Right? Do you see how this works? This is called the method of undetermined coefficients. I actually go through a full example in your course notes. But the idea is, for example, let's say that I want to do 3-point quadrature. Right? So I'm going to have like W1 x1 plus, or f of x1 plus W2 f of x2 plus W3 f of x3. Yeah? Then the method of undetermined coefficient says, like, maybe I want this to hold exactly for small degree polynomials. So in fact, what we're going to do is choose 3 different polynomials f, plug them in, and set them equal. So let's say that we choose f1 of x equals 1. That's a function, right? So that's going to give us that w1 plus w2 plus w3 is equal to what? Well, the integral of 1, let's say that we're on the interval 0, 1, because that's an interval that I can do overhead. Right? The integral of 1 from 0 to 1 is just equal to 1. Yeah? Similarly, if we choose f2 of x to equal x, right? Then we'll have, w1 x1 plus w2 x2 plus w3 x3 is equal to the integral x from 0 to 1, which I believe is a half. Is that right? I think it's right. And finally, if we choose the third function, f3 of x equals x squared, and w1 x1 squared plus w2 x2 squared plus w3 x3 squared, and that's going to be 1 thing. Yeah? So now this is, let's say that somebody has fixed the x1, x2, and x3, so somebody just has decided these are the places we're going to sample f, right? Then this becomes a 3x3 system of linear equations that gives us the quadrature scheme that's going to work for polynomials up to degree 2 exactly. Yeah? It's called the method of undetermined coefficients. Right? Now, what Gauss noticed, which is clever and a little horrifying all at the same time, is that maybe in some applications we actually can choose where we want to query f, right? In other words, the unknowns, so the unknowns in the method of undetermined coefficients are just the w's. But now, Gauss says, okay, well what the heck, we're going to make the x's unknown too. Yeah? So now instead of 3 unknowns, we have 6. Right? In other words, this is saying that I get to choose where I'm going to sample f to get the best possible quadrature. Yeah, do you see this trick? And so in Gaussian quadrature, how many f sub i's do I need? Well, now I have 6 unknowns, w1, w2, w3, and x1, x2, and x3. Yeah? So in fact, I can make this thing work for polynomials up to degree 5. Yeah? But there are 2 catches. They're always up, right? So the first catch is that you're going to have to solve this really weird system of equations for the w's and x's. Right? Notice this isn't linear anymore. We have a product of 2 unknowns. Yeah? In fact, we have like weird polynomials. It turns out there is a theory that develops how to solve these things. And if I'm feeling particularly angry on Sunday night, maybe I'll have you do a couple examples on your homework. But that aside, what it buys you is that this is a very high quality scheme. You know? Now, one other drawback, which is slightly less obvious, is let's say that I have, I use my 4-point Gaussian quadrature scheme, and I notice that I'm not happy with my integral. I think it's a bad approximation, right? It's still an approximation, I think it's bad. So I want to add a 5th point. And the question is, where do I add that 5th point? Yeah? Because I can evaluate f anywhere I want. Well, unfortunately, the solution to this system of equations for 4 points and the solution to this equation for 5 points have nothing in common. So you can't reuse any of your data. You have to resample all 5 things if you want to continue to get this 2n quality that you have from Gaussian quadrature. Yeah, that's kind of a weird setup. So in other words, we say that Gaussian quadrature is not progressive. You can't add sample points in a nice subdivision way, although there are some theories that try to reconcile these. All right. Another strategy you could use, which I'm just going to kind of sketch, would be the idea of adaptive quadrature. And the idea here is that, okay, well, what information have we used? For the most part, we've designed w's, and then we made our x's, some degrees of freedom. But really, we get some feedback, right? That is, what we could do is choose an x1, probably the midpoint, for lack of better x1. And we could say, okay, well now we have a value at the midpoint, and we could kind of look at the quality of our integral. And if it's not good enough, we could adaptively sample f of x in places where we think that f is kind of busy and needs more attention. Right? So in fact, this is a recursive algorithm. It's actually pretty clever. Hopefully I can erase this stuff if anybody's still writing now. Yeah, it's on YouTube anyway. I'm telling you, my cloud score is through the roof. I don't even know what that is, but it keeps emailing me. Okay. Right. So I think your book uses an example that looks kind of like this. Let's say I'm trying to integrate this function, okay? And I divide my guy into intervals like this, right? Probably somewhat smaller to begin with. Yeah. Well, somehow in these intervals, right? These data points look pretty nice and are very low frequency. So this is telling us that f is kind of boring out here, right? And one way to see that that's very concrete is if I run the midpoint rule and the trapezoid rule at the same time, for example, I'll get more or less the same value in each of these intervals. Yeah? But what happens if I run the midpoint rule or the trapezoid rule in these two intervals? You'll get very different numbers, right? Particularly that versus this. Yeah. So if I run 2 different quadrature schemes and I notice that they don't agree, then this is a good indicator to me that something funky is going on in that interval. Right? So what adaptive schemes do is they say, okay, then recursively we're going to divide these in half, and maybe these guys in half, and so on. Okay? So that's all adaptive quadrature. It's very simple. Usually this is kind of an engineering construction. It's a bit hard to make an adaptive method with good guarantees. Yeah? Cool. So anyway, this is all to say that you can make quadrature methods arbitrarily kind of complicated, right? By adding different subdivisions and using these fancy Gaussian stuff. For the most part, 99.9% of the time, you just uniformly sample stuff, add them all up and average, and you're going to get something pretty nice. Yeah. So this is for like the 1% that strategy fails on. Okay. Of course, in reality, a lot of times we want to integrate functions that are of more than one variable and maybe output more than one number. There are lots of strategies for that. The simplest strategy is the iterated integral, which is actually, I believe, how Math 51 introduces multiple integration anyway. So let's say that I have an integral like this. Right? So now this is of 2 variables. Well, one thing you could do is say, okay, well, if you kind of group it like this is now an integral in a single variable, right? Just an x. So I can apply one of my favorite quadrature schemes to this, and then think of the output of this little bracket here as another function, and then apply a second quadrature scheme to integrate in y. Yeah? This is called iterated integration, and it's a very effective, easy to use strategy. You have to be a little bit careful because the error terms multiply here. So if you want, so you're going to have to sample it pretty densely. Yeah? In fact, in general, you have a weird curse of dimensionality, which says that as n gets big, like as I'm integrating f over bigger and bigger dimensions, not only is my dimension getting bigger, but in fact the number of points I need to get a reasonable integral scales exponentially. This makes some sense, right? Somehow you've got a lot more space in a high-dimensional object that you have to explore to get a good approximation of a function. Yeah? Another strategy, which we kind of talked about last class, would be to take your domain omega here and just fill him with triangles or tetrahedra or boxes or something and integrate inside of each of those pieces. Right? This would be sort of the basis function approach. And in very high dimensions, there's a strategy which is probably actually the easiest, which is called the Monte Carlo integration strategy. And the idea here is you just randomly sample points in omega, right? And at each of these randomly sampled points, we evaluate f of x and average them the proper way. And what comes out is that it actually converges to the integral in a way that looks like 1 over the square root of the number of points you have. But the nice thing here, so this is actually very slow convergence, right? We don't like square roots in our convergence rate. It's actually, I think, the first time we've seen this. The nice thing is that it has no dependence on what dimension you're in, right? So remember these weird machine learning setups that I mentioned at the beginning of class, where you're integrating over like a bajillion, you're like trying to find a marginal probability distribution over like 4,000 variables at a time. In that case, this Monte Carlo strategy makes a lot more sense than trying to like very carefully select out points inside of that very high dimensional space. No? Cool. How much time do we have? Okay, you know what, we'll continue next time too. But yeah, so one last question you can ask is, what is the conditioning of the quadrature problem? Yeah, the same question that we really should return to more often, but we only kind of return to it in 205 when it's easy. So in particular, one question we could ask is, not only do we want our integration schemes to be accurate, we also want them to be stable. Right? And this is where the idea of interpolating using high degree polynomials comes in. Remember, in fact, like if I use like a 10th order Newton Cotes scheme, from that delta x perspective, it's going to look awful good. But we kind of know that interpolating things with high degree polynomials shouldn't look good. Right? So there's a second type of analysis that we're going to need that'll reveal that fact. And that's to look at the condition number of using different quadrature schemes. In particular, remember our quadrature formula is basically just some linear combination of our samples, and we can write it like this. Mod q applied to our function f minus q applied to f hat divided by, and in this case we're going to use the infinity norm. I'll explain what I mean in just a moment. Okay. So f hat we're going to say is some perturbation of f. So I change f a little bit, and now I want to know what the effect of that change is on the integral that I get from quadrature. Yeah? So do you guys remember what the infinity norm of a vector is? Yeah, way back to like week 2, right? The infinity norm of a vector is the biggest absolute value of any number in the vector. Yeah? So similarly here, we're going to say that the infinity norm of a function, mod g sub infinity, is equal to the max over all x that are in the domain of mod g of x. Yeah, so just the biggest value that it takes. This is like a fancy way of writing a very simple thing. Okay, so do you agree that this ratio is sort of the change in quadrature over the change in f? Yeah? So, we'd like to simplify this number. In fact, we can. At least we can bound it, right? Because we know that we have a formula for the quadrature, right? This is nothing more than the sum over wi of f of xi minus f hat of xi. That divided by the infinity norm again. Yeah? This is just by definition of q. Remember, q is combining all these numbers. So if we apply, so we talked about this in office hours this morning. Anytime you see like an absolute value around a sum, your brain should just be like freaking out to move that absolute value to the inside and apply the triangle inequality. Yeah? So in fact, since I suffer from this condition, we're going to do exactly that. And in fact, you get now that this is the sum over mod wi times mod f of xi minus f hat of xi, all that divided by f minus f hat. Yeah. Okay. So this is the difference of two f values at some xi. Right? So this number is clearly less than taking the max of this difference over all the x's. Yeah? So this is the same, so you can think of this as being upper bounded by f minus f hat infinity norm. Yeah? So in particular, this is less than or equal to the sum over I, mod of the I, which is not what I wrote in the course notes. That should be a 1 norm, and I will fix that when I get home. Yeah? So what does this tell you? This tells you that the conditioning of your quadrature, right, the sensitivity to perturbations in F, is relative to the size of the coefficients in your quadrature scheme. So the way that you can see that using Newton cotes, for example, with very high order polynomials is bad, is what ends up happening is that the weights that you have to use for that interpolation scheme go off to infinity. In fact, the more terms you add, the bigger they get. Yeah. So your scheme might be very accurate, but it's going to be very, very sensitive to small perturbations of your function. Okay. So now, in the remaining 15 minutes of class, we're going to start talking about differentiation. And basically, some version of discrete derivatives is going to be the topic of the rest of 205. Right? Because we're going to start by how do you compute derivatives, and then we're going to plug these formulas in to schemes for solving differential equations. Maybe we'll even talk about clock simulation or something for fun. Okay. So the problem of finding a derivative is sort of philosophically more difficult than integrating. And what I mean by that is that if I take the integral of a function over larger and larger and larger intervals, right, that number sort of stabilizes. Right? Somehow the wider my integral gets, the less effect that any single point has on it. Right? But derivatives don't have this property. When I differentiate a function, I only care about some itty-bitty neighborhood right around my feet. Right? In fact, so this is a very unstable thing. Your textbook, for example, shows two functions, something like this and something like this. Right? Obviously, these two guys have the same integral, more or less, but not the same first derivative whatsoever. Yeah? And so this can be a very unstable problem. It's very sensitive to sampling and all the things that we don't like to deal with. By the way, I mentioned that multidimensional problems are not so hard. In fact, if you want to approximate the derivative of a function from Rn to Rn, usually you think of this as just a bunch of little functions from R to R, and you do the derivative one at a time. Yep, that's sort of state of the art, I think. It's very difficult to estimate multiple derivatives at a time, as you can imagine. Okay, so the one case when differentiating a function is ridiculously easy is when your function is written in a basis, because just like integrals commuting with derivatives, also the derivative, just as integrals commute with summing things up at a basis, derivatives do as well. Yeah. So in particular, if f is the sum of ai times phi I of x, and f prime is the sum of ai times phi I prime. Yeah? Easy enough. In particular, what this means is that you can think of the phi I primes as a basis for derivatives of functions written in the phi i's. This is kind of a funny way to think about life, but it's actually very important in the field of finite elements analysis, which we'll probably sketch out in a few lectures because I like it and I'm teaching your class. In particular, let's say that I have a piecewise linear function, and I take his derivative, right? Then on each interval, the first derivative is going to be piecewise constant, right? So somehow, so integral is positive, and then it's negative, and then it's a little bit positive, yeah? So somehow the certain interpolatory schemes, like piecewise linear interpolation, has this really funny property where when you differentiate or integrate it, you get a different interpolation scheme, right? Going from piecewise linear to piecewise constant, but it's still sort of in the same class of things, right? And so what finite elements is going to do is it's going to notice that if I solve a differential equation, for example, like I differentiate twice in x one time and twice in y in another, as long as my bases kind of line up when I apply these different operations, then I can still write equations down. It's actually, it's kind of a clever construction. Okay. So how do we approximate derivatives? Well, we know the definition of the derivative, right? It's just this what do we call this? The difference quotient, right? F of x at some place displaced by h minus f of x divided by h. Yeah. Hopefully this formula is like second nature to you guys. No? Just this slow. So obviously what we're going to do is just approximate this with taking h to be a positive number rather than taking 1. Yeah. There are lots of ways to do this. Right. And just like we talked about the quality of our integration schemes, we have to talk about the quality of our differentiation schemes. And this is, yet again, another kind of subtle point. So for example, let's say that I use this forward differencing scheme here, kind of the most obvious formula. Yeah, then what happens? Well, we know that f of x plus h is equal to f of x plus f prime of x times h plus 1/2 f prime prime of x times h squared plus dot dot dot. Yeah? So in particular, if I subtract off f of x and divide by h, right, then what happens? Well, this implies that f of x plus h minus f of x divided by h equals what? Well, this term goes away, this h goes away, right? And you're left with some h squared here, yeah? So what did I just prove to you guys? I proved to you that this approximation, when h is positive and finite, so it's non-zero, you're not taking a limit, is an h squared approximation of the derivative of f. Yeah? Oh, oops, no it's not. It's an h derivative because I divided by h, yeah? Right. Sorry about that. Yeah. Okay, similarly, you could take a backward difference, you could flip the sign of h, and obviously you will also get an O of h approximation. One interesting question you can ask is, can I do better? And the answer in this particular field is always yes, actually. So for example, if you take the centered difference approximation of f, then you get a second order approximation, and maybe we'll prove that and then call it a day, depending on time. So to do that, it's actually quite simple. What you do is you also write down the Taylor series for f of x minus h. Right? So he's equal to f of x minus f prime of x h plus 1/2 f prime of x h squared, and so on. Yeah? So, if I take this guy and I subtract this guy, right, we kind of, you know, we have in the back of our heads that we're aiming for this formula here, right? So if I subtract these two guys, then we get f of x plus h minus f of x minus h, right? Well, the f's go away. These guys add constructively, right? So now you get 2 f prime of x times h, right? Plus, and then these two terms cancel because we subtract. Yeah? And in fact, I'm going to add one more term, right? So it's going to leave 1/3 f prime prime prime, right? That's what happens in the next term. And so in fact, you'll get 1/3 f of x h cubed. Yeah? Did I do that right? No, I didn't. 2/3. Okay. Let's type on notes again. You can see as I got more tired, there are more typos. Okay. So in particular, if I divide this, if I divide this whole thing by 2h, then I'm going to get an approximation of f prime, right? So we can now get rid of this, this 2 and this 2, right? And that becomes a square. And this shows us, you see that this is a quadratic term. So in fact, when you use the centered difference, so I look forward and plus h and then backward and minus h and divide by the width of that whole interval, then I actually get a better approximation of the derivative. This sort of makes sense, right? It's symmetric about x, whereas the last two, the forward and backward difference, kind of only looked in one direction. Yeah?